I'm mostly trying to introduce tools, okay, more than results. So I've chosen some result to introduce the tools, but my goal is mostly to show you the tools. And I've made some choices. Unfortunately, I would say, I think I've got everything that could connect my course to the other courses. So in particular, okay, I'm around to discuss. If you are interested by the thing I'm not introducing, please tell me, we can discuss. Okay, like it's, in particular, I would say nothing about Hamiltonian and dispersive equation, no TDV, no Schrodinger. Okay. And nothing about application to fluid, fluid or plasma, and nothing about self-similar solution. Okay, so then I've got any connection with other courses. Okay? I'm safe. In a way, but we can discuss. Okay, I've done a few things in this direction, but we can discuss the same if you are here for that. Okay. So this is the outline of my course. Okay, like this is today. I discuss dimension 0. I mean, what it is, and then during the next course, I will discuss mostly periodic problem weights. Then probably discontinuous solution. And if I have some sufficient time, I will discuss also France. In the limits where we go to discontinuous. What's the goal? Oh. So today, as I've already said, mostly ODs, but first I'd like to introduce some of the tools for spectral and linear analysis. Of course, I will just say a few things. We probably written a few lists of the books. Okay, after it was discussing this in detail. So I'm just giving you an overview of this kind of things. And I've tried to point out which is the kind of specialization of each of the book. Depending on what you are interested in, you could pick one or the other. Let's go. My first thing is mostly about functional analysis. Related to time evolution. Just speaking with some definition about what I call a linear evolution. In the play role of time and linear time evolution. Sometime. Then there's a bit some solution of that one. And let's think for a few days. Time zero will be the initial time. So first, that's how. Then this is a want to go from time 0 to s plus p, and just do it from 0 to s, and then from it's like the group of. The last thing is looking for some opportunity in time, but only when I apply it to some problem. Yeah. Then when I have a linear equation, I can associate an equation. not know what to give you the equations. It's not defined on everyone, it's only defined on the one which is that equation is differentiable. Yeah. Now, the next thing is at this stage, this is only a notation. I'm not claiming that there's no way. I mean, okay, there's no exponential map in a way, but I'm just saying that this is the way, this is a linear allocation. Right? Then maybe I start with just a silly example, but I think it's give you already an idea of things that could be true and the one that cannot be true. Let's take NP on finite. The simple time evolution just by translation. Then there's a generator. I specifically want to kind of trivial relation, but that gives you an idea a bit of what is going on. I claimed that it was giving you the equation. The generator, and then you have an equation at any time. But really giving you the equation. So you, but not for everyone. You need some kind of regularity, and the regularity is measured in terms of the domain of the operator. Some property associated with A that you get when you are a generator. So coming from this, from the fact that you have some continuity property for the time evolution. You get some properties for the it's not any operator, there's some properties. That's defined. It's mostly coming from the fact that you have an evolution in time, it's continuous. If you do time averages, but you do something that is differentiable in time, and that belongs to, because of that, it belongs to the domain. And then, okay, with some average, you can approximate anything. So that's a way to check that the domain is dense. So doing time averages on the evolution gives you more regularity. Some estimation. Then it's close. I'm saying this mostly because I'm interested in the reverse direction. Okay, I'm doing as if I had this linear evolution, and then I derive an equation. I like to do the reverse. Okay, so I like to take an equation and solve the equation. This is what I will explain now. when can you solve the equation? I give you some operator. What are the conditions? Yoshida. So when do you get linear evolution associated with the operator? There are two conditions in a way. One, many ways to write it. I'm using the formulation that is kind of related to numerical analysis. Which way? I'm asking for the fact that if I take identity minus delta T A with delta T small, this is invertible. And in terms of spectrum, that's the same as saying that 1 over delta T is not in the spectrum. Okay, so the spectrum is the set of points where you cannot invert. So it's another way to say this is 1 over delta T, not beyond the spectrum. That's by definition of what is a spectrum. This is one condition, and the other condition is that you can see some kind of bound. It's a uniform bound on the power of the universes. I need to get a bound that is a uniform in the smaller bound. So if you know a little bit of numerical analysis, you can guess what we do. Yeah. So another way to say what I'm saying right here is that I need two things. I need the implicit Fourier scheme to be defined, and I need it to be stable, essential numerical analysis. Like if I fix some finite time, then I get the uniform bounds on solving. And if I add this on a finite time, then because I have some propagation property, the bound must be exponential. That's how it works. So this is the end of the infinity, but in this case, the convergence of the Fourier scheme in that and x, the time resolution is given as the limit to if I plug this into there, I get also the exponential bound box. But it's what if I'm going to be implicit Fourier scheme. It's defined stable. No, I don't require consistency. It's already kind of involved in the other. That's not quite the standard way to find books, okay, but I think it's quite big. Another thing about semi books, I think it's something you can connect. what is more common is to find a complex version. This also implies okay, C omega not in respect of, and you also get the bound on the this is if analytic, so it's C sharp, but it's not completely easy to check because I mean, okay, it's exactly a stability for schemes. It's I mean, the thing that is not easy is that it involves all the powers, okay, and uniformly in the small parameter. That's okay, but then there is a condition that is sufficient but not necessarily easier to check. Down. But it's like this with the important thing is constant one. Yeah. Okay. And this means that one bound of power and this thing I can just use that the norm of the power is just the power of the norm. When I get the bound with something to the power n, and this thing is less than the exponent the side. This is enough. So if I manage to put one at n equal one, I'm good. So in practical cases, then what you want to do when you're trying to check that you do generate something. Okay. But then okay, you're on. You are just trying to prove that there's a linear evolution that's really good to take omega very large so that you can take C equal one, because then you go for the one really with one C. So it's not always possible, but it's actually quite often. And then okay, more than that, you are also allowed to change the norm by some equivalent norm. So this is also useful. If you have to check something like this, like that, it's quite equal to one, like by any way. Take omega very large, change the norm, and you need the way you have to do infinity powers and many formulas. Nobody is going to do that. Like, my next remark is that this also gives me a way, and this could be another way of result, to approximate my operator by bounding the there are plenty of good properties for bounding the operators. Like that. not in some years. I don't formally explain that when it's the goes to zero, it's A. You see the approximation of A, it's not. And of course, again, it works. You can also produce a value. It's such a bit of small details, the problem of that. And I mean, but in the end, I want to go back to the general case. After that, I get to spend the problem of that. But no less. I can define the external control for problem. But I can do more than that, and I will explain the main problem I can do. For problem of the operator, they can define any function for them to pay out. They the set of functions that are analytic and label. Like when I do a push formula, I need to I do a wrong thing and trying to do it right. So this is another operator. What I mean by going around the study. Okay. This thing here set. Actually, find hyperplane. Take it as a definition. Over. But analytic properties, it doesn't depend so much on the root. I have to place some condition. Go around the spectrum. and it should be in a zone where we don't have to perform. This is well defined. That's what you expect. There's one that you send to the one as a function. It's the unity for point-wise multiplication. It's sent to identity for the operators. Okay, so far I say nothing in relation to A. But I think that same identity. The fact that it's send a linear combination to a linear combination is kind of obvious. Okay, the part that is not obvious is that it sends a product to a product. Also, that you are sending one to identity and few systems. So yeah, I'm not saying this, but it's unique. But that's a unique such morphism. So if you want an exercise, you can do this. Not so. There we give no correction. Discuss this, but it's yes. 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 It could, yeah. Okay, you're asking me what I should. Okay. I don't know how far you can go. I'm not trying that. So I say nothing about the regularity of gamma. I should say, I mean, okay, at least some things to be able to define the integral and so on. Okay, I don't require much more. Just assume that there is a neighborhood. Yeah. You always find a reasonable gamma which can. That's a good question. Yeah, maybe I'm okay. So yeah, okay, maybe I'm missing something somewhere. No, I know, but I will use more than that. Okay, no, in a second. Okay, like it's not. Oh, you're right. Okay, I'm saying nothing about the regularity of gamma, and this has some implication on what I can do for the. Maybe I brought some imagination about the regularity of the domain in which F is holomorphic. Then thing. And then you get the correct given by that. Power series degrees. And then the example we are, yeah, I like mostly. Yes. exponential function blocks, then that's something but for this, okay, this would be enough. I want to do a bit more than that because I'd like to also be able to define projector. But part of the kind of isolated on the rest of the system. And one thing that you would like to be able to do is to project on this part. And the way to think about, okay, what should be the function? You essentially, if you want to keep this part or erase the part, you'd like to apply a function that's 1 in the neighborhood of this, and 0 in the neighborhood of the other part. And okay, for instance, this is easy to check that this is the projector, okay? Because the projector means that when you square, you get back to yourself. And since I have a functional calculus, I just need to check it for the function. But 1 to the square is 1, and 0 to the square is 0. And so okay, this is a projector. And they also use it to make this. Okay, I'd like to define at some point what it means to be an eigenvalue of finite multiplicity for an operator in infinite dimension. But I don't have a characteristic polynomial, okay, so I have to do a definition that doesn't depend. So I will use this the projector to do this. Finite multiplicity, and I will define multiplicity. And then I can define a projector, and I'm asking for a projector to have finite. Not to be algebraic. I will never say algebraic, but it's just connected images. Another way to say this is you look at what the function I've applied, what is the definition by Cauchy formula. What I've done is I'm just trying to take the residue part of the resultant. So if you look at the map, and it's okay. Another way to formulate that is to say that mostly commenting on production. Let me recover. Okay, some part of the connection from spectral to linear evolution. I mean, that's a corollary of the functional calculus. It should be controlled by the maximum of the real parts, the elements of the spectrum, then okay. So basically, typically give you that if spectrum is on the left hand bench axis, then you can get products. Okay, so if this is negative, make a time small enough, you get exponential. The proof is simple, it's good. Spectrum is somewhere. So we just take some sign on room, and then I'll do some to down. And I get this with think that even in finite dimension, this is the most probably the most straightforward proof once you have a functional calculus. I need to go back now to so many books. Then I want to take these things the boundary operator, go back to unknown to one, but taking some limits. So we use these formulas, manipulate them a bit so that I can take the mix and then get formulas for the unknown. What we do is take the boundary gates, get some proper formulas. So the issue is if you think about the Euclid approximation, the first issue is that the spectrum will get unbound when the current goes to 0, so you cannot use the same form and you have to do. Well, let's use the contour that just sits surrounding the spectrum of A at the limit, and it will typically be in some half plane. So the left. So my contour, there should be the only way they can surround is to just go straight. Right. Do that, and I will take the limit in the base one. and the control that's surrounding the spectrum. It's omega over real bar. To be like close from omega there. Omega. Take the limit up with the limit. Okay, this will give me a straight into one. And I need just to check that the other part is going to zero. So this is true, it's strictly positive because the exponential will go to zero and I can lose some limit conversion theorem. When I do that, in the end, what I get what do we have as one over one thing. Finite, like this is the limit as r go to infinity of the finite integral over finite. It's this is not an integral function. Take a norm here. No, take a norm, because we believe. Mais the fact that it's well defined is kind of connected to the fact that it is oscillating more and more. That's really a new problem. Yes. At this stage, not. Then you don't like complexity when you describe it as real. Just comment, right? Yeah. And when I parameterize, it should be kind of more obvious that it's only already before and see I'm integrating against something like this, so I'm always trying to do some Fourier analysis or something. But exactly. To complete the Fourier analysis, we'll also care a bit about what happens for negative point. Yeah. So now, okay, now I'm just looking at this part. Okay, there's no. Okay, just looking at this part, but for the same reason that the dotted part is going to zero in positive time, this one is also going to zero in positive, like negative time. So it's just going to be in zero. So if I do a negative integral with 0.7. Which is that I have I'm doing linear and for the transfer. the same as saying that by definition, what you're saying evolution. Okay, like they only define positive time. Then they have the right to go exponential. And because of that, more or less you need to allow more exponential, but you should go in. Using Fourier, you have seen that I'm fine. So if you're trying to use exponential and not blow up, there has to be for something pure image. And the only go positive in time, you can let it go on one side. Then you have some freedom about what is the omega should use. If you don't want to fix some omega arbitrarily, you will all then you will have a okay. Give you the things. Simply why spectral theory is very much connected to Laplace transform. So for the time evolution, this is the same thing. And the Cauchy formula I've shown you before also explain why we care so much about spectral theory, because essentially you can get back any function of A just by knowing the spectrum. It's a formulation that I can use for unbounded operators changes. Okay, not if it generates, I'm only assuming that it generates. An assumption. And this formulation with an integral, the vertical integral works when I have some with enough regularity to make the postmodern. The domain of the you may wonder why A square, essentially because more or less you are trying to get some kind of identity by expanding this guy over 1 over Z square. Once you try to do that, put some power. You need to do it twice. There's a power plus A square. And okay, so another thing that since it is a bit like Fourier, you should expect that it's my operators, they are very much like Fourier multipliers. So I go to Fourier, I multiply by something, I go back. Okay, so this is the time evolution, more or less. And then, but for Fourier multiplier, it's very easy to check if they are continuous or not. Because if, okay, on L2, for instance, being continuous as a Fourier multiplier, I just like to multiply by something that is bound. The norm from L2 to L2 is the infinity bound of the multiplication. And then, okay, you should get something like this too. Okay, so there is a theorem like this. I will just write it now. So things tell you new, but if you control uniformly the regular one, then you get the bound. So it's not replacing the Hilo-Yoshida theorem in the sense that it looks like a simpler version of Hilo-Yoshida. So it's not because I'm already assuming that it's generating a symbol. Okay, so it's just improving the time evolution bound. Okay, so it's to prove that you generate someone, you can take an omega that is very large. But then if you want to know long time, you would like to take the omega as negative as you can. Okay, so this is a way to do that when X is a Hilbert space. Okay, so it's like there are some extensions. I should give name. So it's like, so in my opinion, it's a bit like Parseval. That's what is behind what I've explained about Fourier multipliers. It's just Parseval. So it's a bit like Parseval, but the structure of the name. If you can use it, then you should use this because that's the work. By far the simplest of the theorem given something about large. Okay. That's all for fundamental analysis.
So sorry,
Yes.
I heard about this. I really don't really see. So does this C, let's say, in the estimate,
Yes.
depends on the.
It depends on the bound of the upper bound. Yes.
So it's explicit somehow.
A bit. Okay, the first proof they were not so explicit, but there have been recent proofs where they are improving so that you can get an explicit control. It actually matters because it's also applied in cases where the A depending on some extra parameter, you need to control everything. But there are many proofs now available. Okay, some of them are okay. I can tell you which one I like the best. Maybe off the record.
Okay.
Okay, broadly speaking, I can say that when I say more or less explain why you could get something that is bounded from L2 in time to L2 in time, and then maybe H1 in time to H1 in time. And if you interpolate somewhere in between, you get infinity in time to infinity in time. Okay, so I'm exaggerating a bit, but that's the spirit of some of it. Do some cutoffs to make this work, but this is more or less what one of the proofs. By interpolation between L2 and H1. This is all for functional analysis. Okay. Like to do only in finite dimension. And I begin by we have enough your classical one that you already know, I expect. And I'm looking at a constant solution with you take some value, give the constant solution, if finally that's 0. That's the current space. Attention. The spectrum is on the left. So it's finite dimensional, given the supremum is negative. Yeah. Pick that as those, then you get what we already know is that you also have some control the exponential of the linear part. This is what I've explained before, the corollary. And then I'd like to use it in the equation. So I need also to get, I would think about the equation as being like some affine equation with a forcing by some terms that are quadratic. And I'll write the UML formula or Mike formulation, okay, or variation of constant, whatever you could call it, and do some fixed point. It's bad. I need to control the non-linear term. Something telling me that there are really part that I think that's quadratic is locally quadratic, giving a bound for that. Wow. I need to write bar, bar, for writing the equation for the small part. I think that I think small. Then I write this Like all these are here. Then I need to start it on. So first thing I do is course. This is not the only restriction. Yeah, of course, like that. More than this. Chosen is just better way to get that after the time evolution. I will still set aside the constraint to apply the quadratic bound. Yeah, I will not give about this part because I want to discuss more the next part. Okay, so let me stop here. I say leave the next slide. We just say that there are two ways. Actually, either you can do a fixed one with norm including the exponentials, or you can use a continuity argument. Meaning that you already know that the solution exists on some time interval that is maximum. So you only need to prove that you can get a bound. And one way to do that is to prove a bound that tells you that if you are small, you are extra small. So that's a way to start. Like, okay, you insert this that you're small here, you use the equation, and you get back that you are extra small. If you are able to do that, it tells you that the time interval in which you are extra small is both closed and open. Okay, the fact that it's closed is typically due to the fact that you are putting inequalities with equality involved. So that's fine. And then open is just that if you are extra small up to some time, then you are small on a slightly larger interval, and then you prove that when you are small, you are extra small. You are, okay, you are extra small a bit longer. So it's a bit like, I mean, this is called the continuity argument. It's very standard. In most papers, it's not written at all. Okay. I should say, finish by continuity argument. Just this. Okay. It's a bit like a continuous version of induction. Like first time you see induction, it's like crazy. Like you are assuming the thing that you are proving, but you know you are proving it the next time. Okay? Like this is the same thing. You are proving that you get something slightly better than what you got. Okay. We also add that we also know that if the spectrum is contains someone positive or part, there is instability, and that everything else is does not. Any other you can see what is not easy to get into. For instance, we can get an example where the linear evolution is unstable, but not exponential movement, and then see the non-linear dynamics exponential way. All right, it's something to be. Because I want to give another OTA example. And it's to illustrate something that we see quite often with PDs that there could be situations where the spectrum cannot have this kind of spectral gap that we are here, like something that you are on the left and measure axis with a positive distance. And it happened by accident, it also could happen just because of the structure of equation. And I'd like to show you an example of that now. So what do I mean by structure? So in this case, my equation doesn't depend on time. So it doesn't depend on time. So it's I know that for n equals 0, down, when completion equals to that the equation is varying by completion in time. It looks like a C thing, but for solutions that are not constant in time, it's a huge impact. But we've seen some equilibrium. Constant in time, it was not really seeing the fact that it's not in time. But I will do it for now. I try to put stability for a solution that's very non-constant, and you will see that this is an obstacle. Something that we come out. Now, I would say the first thing I'm saying is that any constant is also a very good also from the equation, it's also very good. So it's so yeah, two times can get the equation that are important to see parameter down. There is no gap between the solutions, between family, the smooth family. If I differentiate the number family, I will see something for a linear equation. So just plus the side of the constant of the equation and differentiate with respect to T0. What you get is that limit of eliminate the operator machine. And what I'm saying is that I have the solution of the linear equation that's given by the translation. Well, time derivative is solving the linear equation. It's just coming from the fact that the translate was solving the differential effect of the translation values. And I'm saying that this gives you an obstacle to the exponential scaling just because the scale is very. That is not. If you think that the linear equation give you some kind of discounting, this is impossible to subtract because of the process. Correct. There was a linear equation. Let me even into the time evolution, so it's not time independent going into that as well. It's something that can be able to move from some time to another time. What I say that since we know way to say that that's one belongs to the spectrum. The evolution after one period. I don't know. Another way to say what I say about the fact that time derivative solving the equation needs variables. So between like if I put this into the equation, I solve when I look at after one period, I just get back to work. Like this. In general, c'était en mode, vous mettez la function, what can I say? C'était en mode function. We can assume that function one is whatever. Then for one guy, so it's not difficult to guess what you can expect. I expect. But after that, when you do perturbation, maybe you can go to a solution fast. The perturbation says that the solution will go faster than the verification. Or slower. So then you move around to some other state. Maybe in advance, and maybe delay, I don't know. When you do that, the perturbation in the shape to maybe slow you or make you go faster and you accumulate the translation in time, you're taking some delay. And there's nothing to put, nothing is pushing you back to the reference you started with, because all the topics are good solutions. There's no reason to pick one instead of another one. And then the only thing you can do is trying to find what's the best one for you, just in time, and move along. So this is what I'm thinking about stability, it's called orbital stability, because what you are looking at is not so much the stability of one solution, but it's the stability of the orbit of the solution under the action of the symmetry. Okay, so in this case, the symmetry that the time rotation, you're saying, okay, but this stable really is the solution under the action. So what you can prove is exactly that. There is a certain shift. And for here, then the time shift is accumulated with the derivative. And it's coming from the fact that your shape deformation is not small enough. So accumulating at the rate that is itself decaying when you converging. And there is an asymptotic shift in space. There is a limit. Right. Converging to strong one. If someone is not far from being zero, size is not moved by So you just know that it is small. Okay, so just combine it's well, activating something without controlling it. But you know that in the end, there will be some elements of it. Yeah, can say that. There is some of the sort of that is due to comparer. I'm not sure it is. Because it will be that is going by comparison. Okay, this is not the one I would like. The right is proof that it's simply the proof that I do for waving. Showing this example to give you an idea of how I think the job in the complete context. But this is not the example. But I know no group where it's
So just was, but so do you need somehow that one is isolated from the rest of the spectrum?
yeah, it's finite dimension. So it's so there's always a gap because we have infinite dimension. Yeah. So that was the same for the Lyapunov theorem. I say that it should be on the left, but I really mean that there's a gap. In finite dimension, there are finitely many eigenvalues, so it's fine. So I mean, my guess is that you can reproduce this argument in infinite dimension if you have a gap. Okay. But I mean, the partial generalization and a bit later is in a case where there's no gap and it's part of the central spectrum. It's not sure. Next time. The first thing I have to explain about the proof is what is the linear counterpart. Okay, so what you should first do is you look at the linear evolution, you pull out what is not decaying, and you get decay for the rest. Let's find the composition of the evolution. There's a part that is not decaying, and the part that is not decaying, we think that it should be something like the time derivative. And that's the fact that should be decay. And it goes from project one. Okay, that's the projection of that. Then the remaining part. But the linear level, I'm trying to say, okay, anywhere I can, I would say quite the phase. So this should be like a phase shift, this thing. And this is the way you translate at the linearized level. It's just coming from differentiating the family of translate, so it's just giving you the shift. And then this should be decayed. And also, okay, I need this to be well done so that I don't need to do it constantly. So that I start condition that I right now can forget about those first reading. That thing that once it's done, it's done. Type up. That's an idea. So I just need to define L. Okay, once I have L, then the S type is defined by the first equation. And then I need to check the properties. What I will do is I write the projector on one of being. Okay, so I know that it is something of rank one in the branch generated by this guy. So I know that there is some that we have. It's given by you see the projector of rank one, and it's range generated by this guy. The test is three. Then I need to do the time evolution. The time evolution of this guy I already know. So I just need to do the time evolution of H0. And I must simply do it in such a way that I don't change the scalar product of anything by the time evolution. That's a way. That's a way to somehow freeze the scalar product. When you act on this guy, but it's just the time evolution of someone, it will give you just a scalar product at initial time. Then I define all the rest like this, and the decay property will come from the fact that we just look at the your technology is inside the inverter. So this is power, we get some decay, and the other thing you need to know is because you have some kind of periodicity, the time evolution back and forward. Want to power production, people need to understand this. I mean, but from the simulation together, you will get the thing. That's much more of this. What is the dual formula? You need to study. Then I will start with that. Your unknown are the phase shift, but also the deformation of the shape. Look at my mirror. Instead of considering you as an unknown, my unknown medium size. We plug this into equation and look at the equation and think that psi and v are my own. First computation will get shaped like this. But I should think that v and psi are the unknown. Okay, when I want to pick out the linearized part, I'd like to think about the linearized part as being the part where there is either v as linear or psi as linear. If you do this, after some computation, you see that the linear part of the equation is just this. At the end, they are quadratic. I don't care so much about them. The important thing is that the linear part can be written this way. So it's kind of obvious for V. Okay, actually, if you look at the V linear, it's, there is no V here. Then you should forget about this. You expand it. It's even before. The part that is not obvious is psi. Here I'm using, okay, so the linear part in psi, so psi prime times V of U bar. The V of U bar is d over dt of U bar. Okay, so this is starting to give me this psi prime d of dt of U bar. But the part is missing. The part that is missing is exactly the linearized equation applied to the time derivative of U bar. So it's once I'm here, I can do the pyramid formula. So I write the pyramid formula and I will split the choice to do. Okay, so if I just write the pyramid formula, I will get that this guy is equal to something, but this is not what I want. I want to separate V from psi. Okay, so that I get two equations. Time equation for V and time equation for psi. I have to make a choice of this thing. It's not equivalent. I will use just the splitting of the thing group that I had before. I write the pyramid formula and I split. Get the V of U in the then this part we take the rest. Okay, the part that is like d over dt of U bar times L of something. I can erase the d of dt of U bar, and then I get psi as being the L part. What I get when I do pyramid formula, I do the thing and I erase the derivative. Okay, so then I'm essentially done. It says that there is a mistake there. Something is wrong. It was a question that was wrong. Not really, it's given like the time decomposition. Here I have the wrong initial data. But when writing this, I have more or less assumed that psi of 0 is 0. If I do psi equals 0 in here, this would be 0. Then I'm left with something here. This in general, this is non-zero. So I mean, if I solve this, I'm not solving the initial problem. But enough right to put in reality. Then I need for this. And the separation only for a long time. For short time, I can do whatever I want. Okay, then I can do some kind of convex combination between doing nothing, solving the standard German formula, or doing this. And there are many ways to do that. I can do it with this guy here. It is 1 when the time is long, and it's 0 when the time is short. Then I have a good initial data from psi. And I have a good decomposition in long time, and I can do a fixed one. The important thing is that this is the MC prime that are defined. You do the fixed point, you have to do it in B and C. This is C prime with non-linear. C prime is decaying, psi is not decaying, it's relative to point. You write the complete details of that, you need to do the fixed point and B and C prime. Yeah, so for the others.
Okay, thanks, Luis. I don't know if there are some questions. It's just something that I did not get it. Let's say, what should you put inside this red bracket that multiplies 1 minus chi?
The initial formulation of gravity.
So, yeah, okay.
The piece of the data is right. In enough long time, you get the separation.
If there are no more questions, I think we can thank Luis again. So the first lecture. Okay. I don't remember that. Yeah. Okay. So yes, as Stefano was suggesting, for all students, if you need, there's also some a meeting room upstairs that you can use to study or to discuss or but yes. Yeah.